The overview covers core concepts in machine learning and image recognition, including the implementation of a single-layer perceptron and its training algorithm, highlighting its ability to learn from labeled examples. The delta rule is explained as a method for updating network weights to minimize error. Support vector machines are compared with neural networks for image recognition, outlining their strengths and weaknesses. Real-world challenges, such as variations in lighting, occlusion, and image quality, are discussed for their impact on recognition accuracy. The history and evolution of perceptrons are traced, showing how modern neural networks have addressed their limitations. Finally, hybrid models combining neural networks with other learning algorithms are introduced, illustrating how these approaches can enhance performance in specialized applications. Backpropagation is a core technique for training multilayer neural networks, allowing these models to learn complex functions through systematic weight adjustments. This method is underpinned by the universal approximation theorem, which states that a feed-forward neural network with at least one hidden layer can approximate any continuous function, provided it has a sufficient number of neurons and properly configured weights. The backpropagation algorithm utilizes gradient descent to minimize error by propagating the loss backward through the network, iteratively refining the model's parameters, and enabling the network to achieve progressively higher prediction accuracy. In addition to backpropagation, cross-validation is essential for assessing the performance and generalization capability of neural networks. By dividing the dataset into training and validation subsets, researchers can ensure that the model performs well on unseen data rather than simply memorizing the training examples. The discussion also explores radial basis function (RBF) networks and their associated training algorithms, highlighting an alternative approach to function approximation. RBF networks employ radial basis functions as activation functions, offering benefits such as faster convergence and effective handling of nonlinear relationships. Examining RBF networks provides valuable insights into their unique strengths, contributing to a broader understanding of neural network architectures and their practical applications across diverse domains. Uncertainty and vagueness play a critical role in a wide range of real-world applications, particularly in systems where data is incomplete, ambiguous, or imprecise. To address these challenges, the introduction of fuzzy membership functions is essential. Unlike traditional set theory, which relies on strict binary classification, fuzzy membership functions allow elements to belong to multiple sets simultaneously, each with a specific degree of membership. This approach provides a flexible framework for modeling and reasoning about complex systems, enabling a more nuanced and realistic representation of data and relationships. By incorporating degrees of membership, fuzzy logic facilitates the handling of ambiguity and partial truth, which is especially valuable in areas such as decision-making, control systems, pattern recognition, and expert systems, where human reasoning often involves imprecision and subjective judgment. The use of fuzzy membership functions allows computational models to mimic human-like reasoning, improve interpretability, and make more informed decisions under conditions of uncertainty. Moreover, this approach enhances the ability to model nonlinear relationships and dynamic behaviors in complex systems, providing a robust and adaptable methodology for tackling problems that traditional binary logic cannot adequately address. Fuzzy logic provides a powerful framework for reasoning and decision-making when dealing with imprecise, ambiguous, or incomplete information, thereby enhancing the quality and reliability of decisions in complex systems. By allowing elements to belong to multiple sets with varying degrees of membership, fuzzy logic enables a more nuanced representation of uncertainty than traditional binary logic. This flexibility is particularly valuable in modeling real-world phenomena, where data is often noisy, partial, or subject to interpretation, and where human reasoning frequently involves ambiguity and subjective judgment. Building on these principles, fuzzy clustering algorithms such as fuzzy C-means and possibilistic C-means extend the concept of membership to the grouping of data points in unsupervised learning tasks. Unlike traditional clustering methods, which assign each data point to a single cluster, fuzzy clustering allows each point to belong to multiple clusters simultaneously, with varying degrees of membership, reflecting the inherent ambiguity in many real-world data sets. These algorithms are widely applied in areas such as pattern recognition, image segmentation, and data mining, where they improve the classification of datasets with overlapping or unclear boundaries and enhance the interpretability of results. In addition to clustering, fuzzy classifiers, including fuzzy k-nearest neighbors, provide robust methods for supervised learning in environments characterized by uncertainty. By incorporating degrees of membership into the classification process, these models can better handle noise, outliers, and ambiguous instances, resulting in higher accuracy and more reliable predictions across complex data sets. Such approaches are particularly useful in applications like medical diagnosis, financial modeling, and environmental monitoring, where the input data is rarely precise or complete. Furthermore, fuzzy measures and fuzzy integrals offer systematic tools for quantifying uncertainty and integrating fuzzy information into coherent decision-making models. Fuzzy measures generalize traditional probability measures by allowing the assignment of importance or weight to different subsets of data, while fuzzy integrals provide mechanisms for aggregating these weighted values to make informed decisions. This combination enables decision makers and computational models to synthesize imprecise information, evaluate trade-offs, and prioritize actions in a principled manner, even when faced with complex and conflicting data. Overall, the study and application of fuzzy logic from membership functions to clustering algorithms, classifiers, and fuzzy measures provide a comprehensive toolkit for handling uncertainty in a variety of domains. These methods not only enhance decision-making processes, but also improve the interpretability, flexibility, and adaptability of computational models, making them invaluable in areas ranging from artificial intelligence and machine learning to control systems, expert systems, and real-world data analysis. By embracing the inherent fuzziness of real-world information, fuzzy logic enables systems to operate more intelligently and robustly, bridging the gap between human reasoning and computational modeling. Fuzzy logic provides a robust and flexible framework for reasoning, modeling, and decision-making in environments characterized by uncertainty, vagueness, and incomplete information. Unlike classical binary logic, which strictly categorizes elements as either belonging or not belonging to a set, fuzzy logic introduces the concept of degrees of membership, allowing elements to partially belong to multiple sets simultaneously. This capability is essential for accurately representing real-world phenomena, where data is often noisy, ambiguous, or subject to human interpretation. By capturing the nuances of imprecision, fuzzy logic enables computational models to emulate human-like reasoning and make more informed adaptive decisions. A central component of fuzzy systems is the fuzzy membership function, which quantifies the degree to which an element belongs to a particular set. These functions allow for a smooth transition between full membership and non-membership, facilitating the modeling of gradual changes and ambiguous boundaries in datasets. For example, temperature, risk assessment, or customer satisfaction are rarely absolute values. Fuzzy membership functions provide a natural way to encode such continuous variables in computational models. Building on these foundations, fuzzy clustering algorithms such as fuzzy C-means and possibilistic C-means extend the flexibility of fuzzy logic to unsupervised learning tasks. Unlike traditional clustering methods, which assign each data point to a single cluster, fuzzy clustering allows points to belong to multiple clusters with varying degrees of membership. This approach is especially valuable in domains such as image segmentation, pattern recognition, and bioinformatics, where data often overlaps or exhibits complex relationships that cannot be captured by hard clustering. Fuzzy clustering algorithms improve the interpretability and robustness of results, helping analysts identify meaningful patterns in ambiguous datasets.